So section 4 is gravitational torque at the center or and the center of gravity. So we're learning about something new called center of gravity. It's not really new, but we're finally using extended bodies. And so we got to talk about center of gravity. So we have this gymnast here. It's a great example. The gymnast is swinging around the higher bar on the uneven bars. And so if you look in the picture, we have obviously there's various parts of the body that are all swinging around the bar together. So each part of the body is having gravity exerted on it. So how does this affect our mathematics as we try to calculate like a gravitational torque? So up here, we have these arms. Up here, we have the person's chest. Here, the torso. Here, the leg. Here, like the calf. Here, the feet. All of those things will add together, basically, all of those individual torques, and give us sort of a net torque. And that net torque is going to occur at this body's center of gravity. And if you notice that symbol there, it's basically a circle with a cross on it. And then we have this shaded and then this shaded. That's our symbol for center of gravity. So watch for those symbols. The net force will be applied at that center of gravity for us. Okay. So the rotation axis is up here on this bar, and then our torque will be applied at the center of gravity, and we're rotating around this way. So relative to our perspective, we're rotating in a positive direction, counterclockwise. Okay. And that torque is being applied at the person's center of gravity. So the weight vector is from there pointed down at all times. Okay. All right. So this body here is responding as if the entire weight acts at the center of gravity, assuming it's a rigid body, which it would be for that person. Okay. So now a 3.2 kilogram flagpole extends from a wall at an angle of 25 degrees from the horizontal. Its center of gravity is 1.6 meters from the point where the pole is attached to the wall. So what is the gravitational torque on the flagpole about the point of attachment? So we can draw a picture using all of that information. So we have the wall, and then we have the flagpole, and it says it's at an angle 25 degrees from the horizontal. So we have the flagpole. So here is the horizontal. 25 degrees up might look something like that. So maybe there's a ball at the end of it. So here's our flagpole, 25-degree angle right here. Now, very important information. The center of gravity is 1.6 meters from the point where the pole is attached to the wall. So the center of gravity is 1.6 meters from the point where the pole is attached. So we go from the point where the pole is attached up 1.6 meters.
So do you draw the symbol center?
Yes, draw the symbol. So here is our center of gravity. I don't know why, but for some reason I always like drawing that. Okay, so now the weight of the flagpole vector will be pointed straight down, and it's coming off of the center of gravity. So there is our weight. Okay, now what do we do? Well, we're supposed to calculate the gravitational torque. So basically just the torque, okay? We're calculating the torque due to gravity. Now, how can we do that? Well, if we so we haven't tipped the axis, so the weight is actually along the y-axis, all right? But if we extend this horizontal thing over, we've created a right triangle there. Mm-hmm. And by the way, which way is this torque applying a rotation? Which way is the torque attempting to rotate this flagpole?
It's going to rotate counterclockwise.
It would rotate
or
clockwise. So this would actually be a negative rotation.
And that's because of the gravity, correct?
Gravity's trying to pull it in a clockwise way, so that makes it a negative rotation, okay? That's just something you always want to think about so that you can apply a negative sign correctly if needed, okay? So what we have going on here is an R perpendicular. How do I get that R perpendicular?
With the 25 degrees. Well, the weight is the perpendicular, right?
So where is the R perpendicular?
It is opposite the 25 degrees. So what?
Is it opposite?
Just it's right there.
This one?
Well,
So our 90 is here.
yeah.
We have our, from the pivot, which is here, out to the center of gravity, which is where the force is being applied, right? That would be our R. So our R perpendicular,
The weight vector.
the weight vector,
Cosine 25.
cosine.
It's the weight.
Okay, so equals 1.6 meters cosine 25 degrees. Right? You guys okay with that?
Yeah.
Okay. If we set up the ratio, we'd have to multiply by 1.6. Okay, so what is this?
Oh, you want to calculate?
Yeah, we need it.
Let me change this to degrees before I decide to do this. Times cosine 25. 1.45.
Okay. 1.45 meters is that length. So now we can use our formula. We know the mass was 3.2 kilograms. We know gravity, so we can calculate the weight. We have our radius already perpendicular, and we have our angle theta already used. So torque equals R perpendicular times the weight. So we have, oh, and it's going to be negative, remember. So we have equals R perpendicular meters times the weight, which would be 3.2 kilograms times 9.8 meters per second squared. It will be newtons from the weight times meters from our perpendicular. So the units of torque are Newton meters.
45.47.
45.4, we have two significant figures, so it's going to be 45 Newton meters. So we have this formula that we're using to calculate the torque.
Where do we get that from?
We have that formula.
That's
We're using that one because it made sense to with the moment arm coming off like that. So we used R perpendicular instead of the other.
the RT.
Okay, so now if we have this situation where we're holding a ruler or meter stick or however you want to look at it, if the center of gravity is below the pivot, so we're just holding the meter stick directly down, then nothing's going to happen. There is no torque. But if the center of gravity is not below the pivot, then we have some component here where we break the weight into components because of this situation that we have here. Then we do have a torque, and the ruler or meter stick or whatever is going to turn. Okay? It's going to seek this state right here where there is no torque. Same thing is happening here. If you ever try to balance a meter stick or a bat or something in your hand, a pencil, then if the center of gravity is situated directly above the pivot, which would be where it's sitting on your finger, then it will balance and it will just stay there. However, if the center of gravity gets outside of your pivot, then it will tip. So the goal is to put the center of gravity directly over the pivot point so that it won't tip. In other words, there will be no torque. Okay, so your goal is to create zero torque so it does not tip. Make sense?
Yeah.
Okay. So an object that is free to rotate about a pivot will come to rest with the center of gravity directly below the pivot point, or above in the case on the right-hand side. If the center of gravity lies directly above the pivot point, there is no torque due to the object's weight, and it can remain balanced. However, even the slightest movement in either direction will create a torque, and the object will begin to rotate. So if you've ever tried to balance something in your hand, keeping that center of gravity directly above it is the trick. And if you can do that easily, then you can balance it. If it's hard to keep the center of gravity above your pivot point, above your hand, then it's difficult to balance and you will fall.
So then what about like when you're standing on one leg?
Understood. So calculating the position of center of gravity now. The torque due to gravity when a pivot is at the center of gravity is 0. So if we have the pivot directly at the center of gravity, there is no torque. Hopefully that makes sense. Use this fact to find a general expression for the position for the center of gravity. So we have this picture here, and this is setting up a very general scenario. So we put the center of gravity at the pivot, okay? So that means that at the pivot, there is no torque. All right, now we have this beam or a bar, and on the one end of the bar, we have some mass, and at the other end of the bar, we have some other mass. The picture is showing that mass 1 is bigger than mass 2.
And the radius is greater.
Also, the radius for mass 2 is greater than the radius for mass 1. Now, we're trying to say that there is no torque here, so mass 1 has to be closer than mass 2. This is like a teeter-totter situation, okay? If you have people on a teeter-totter and one side is heavier than the other, that one side drops, right? But if you move that one side that's heavier closer than the other side, now you got a longer radius, you're going to get a bigger torque, as we know, okay? So finding that radius length that's perfect to balance it back out is the trick, okay? So gravity acts on weight 1 with the moment arm R1, so the torque about the pivot, XCG, we're going to use this notation here for center of gravity, is torque 1 equals R1 W1. And so we can kind of simplify it using this notation here, equals XCG minus X1 times M1G. So then the torque due to weight 2 is going to be the similar sort of logic there. Torque 2 equals negative R2, since this one is trying to turn us this way. This one is trying to turn us this way. So we have a counterclockwise, the other one is clockwise, okay? So this one's negative R2 W2, and then equals negative. So the R2 is now X2 minus XCG. So we're just replacing R with X. M2G. So why is the negative on torque 2? Because it's clockwise rather than counterclockwise torque. Okay, if the system is in balance, then torque net equals 0. So now I can set the two things equal to each other. Torque 1 plus torque 2 equals these two things here. Okay, is that sort of making sense?
Yeah, it's just a lot of new XCG stuff.
It is. But logically or conceptually, you get the idea?
Conceptually, I can see how they equal each other. It makes perfect sense. But now if you were to start plugging in numbers in those positions, probably not.
Okay. Okay, so now we're going to solve that equation for XCG. So XCG is here and here. So we had to do some manipulation, and I spared you all that manipulation because it's some work to get there. But if we solve for XCG, in the end, we wind up with this formula right here. So the position for the center of gravity has to be X1 M1 plus X2 M2 divided by M1 M2.
That looks to be important.
It kind of is. So, because the center of gravity depends on the products of mass and distance, then this tells us that the objects with large mass count more heavily than objects with small mass. Therefore, the center of gravity tends to lie closer to the heavier objects that make up the system. And you can think about that like conceptually as well, like on the human body, for example. Your center of gravity tends to be where the more massive parts of your body are. So your center of gravity is more in the torso than towards your feet, right? Because your more mass is in the torso area, okay? So hopefully this is making sense. X1, M1, X2, M2, those are together. That's not always the case in our formulas, but here it is. And then divide by the sum of the mass on the bottom. Okay? All right. So now, finding the center of gravity. First thing you want to do is choose an origin for your coordinate system. So the center of gravity is not always the same in every situation. You're going to actually have to calculate it on every problem. Okay? So choose the origin for the coordinate system. You can choose any convenient point of origin. Convenient is the key there. We want to make sure we choose a convenient place. That's going to simplify our work. So determine the coordinates for all the particles of masses respectively. So x1, y1 for mass 1, x2, y2 for mass 2, and so on. So the x coordinate of the center of gravity will be using the same idea from the previous formula. This is our guy right here. The x coordinate for the center of gravity is x1, m1 plus x2, m2 plus x3, m3, and so on, divided by the sum of the masses on the bottom.
So the x is the radius.
The x is the x distance from the center of gravity. So if I go back here, the x distance from the origin, sorry. So here's the origin. So here's the origin right here. X1 is here, the distance from the origin. X2 is here, the distance from the origin. Okay. The center of gravity is somewhere along the way. We don't know where it is. Okay. We're trying to find it. So we choose a convenient place for the origin. We just don't know where that is. You might choose the pivot for the origin. Okay. Don't know. You're just going to choose a convenient place for it. Okay. You might choose the origin to actually be this first position right here. All right. That might be a convenient place. The point is, x1 is the distance from the origin, x2 is the distance from the origin, x3 is the distance from the origin, okay? Now, we also have y coordinates as well if we're dealing with more than one dimension. So, but the formula is the same. The y coordinate for the center of gravity in the y direction is y1, m1 plus y2, m2 plus y3, m3, and so on, all divided by the sum of the masses for the y's.
So now, can you have a center of gravity in both dimensions?
Yes. So you'll have an x coordinate for the center of gravity and a y coordinate for the center of gravity. Okay? And then that will put you in space somewhere on the coordinate plane. And then boom, there's your center of gravity. Okay? Good with that?
Yep.
All right. So now Emma and Noah are playing on a seesaw. Noah, mass 22 kilograms, is seated 1.6 meters away from the pivot point. Emma, mass 25 kilograms, wants to sit at a point that will make the seesaw exactly balance on its pivot, because that's what you do when you're playing on a seesaw. How far away from the pivot must she sit? Assume the mass of the seesaw itself is small enough that we can ignore it. Okay.
So let's define the masses. Noah would do his mass 1, and Emma was mass 2. Right?
Sure. It doesn't matter. We can do that. I'm probably going to want to draw a picture, though. So we have our seesaw. We'll put our pivot on here. Usually we'd use a triangle to represent our pivot like that. Now we have our person on one end, person on the other end. We want it to be horizontal. Now we can define our origin somewhere. Where is a convenient place to define our origin?
I think over there.
On the very far left, on the very far right, or at the pivot?
The very far left. So that everything's positive for us.
Okay, on the very far left would make everything positive. My question would be, does it matter if everything's positive?
No.
Not really. On the very far right, everything would be negative. Does that sound better?
Let's do
Not
the
really.
pivot point, because we're already giving Noah the distance for x on his.
Mm-hmm. So, yeah, we are given seated 1.6 meters away from the pivot point. So in reference to the pivot point, right? It makes sense then to call this the origin right here. Okay, so this is our origin. That's 0.
So Noah is 1.6 meters away from that.
Okay, so which one's Noah?
Let's go to the one on the left.
Okay, so if this is Noah, then Noah is actually seated not 1.6 meters away,
Negative.
but he's negative 1.6. And that's fine. We can call him Noah. That's cool. Okay, that means Emma is on the right. And that makes Emma unknown distance. So we're going to call her X.
Do we need to draw a weight force down off of each person?
Okay, so we'll get there. Now, we want the center of gravity to be where?
Right on the pivot point.
Right on the pivot point. That's right. So we want this. We want that to be there. Okay, now we want Noah over here. So the mass over here, maybe I can say mass of Noah is what?
22.
22 kilograms.
Yep.
And over here, mass of Emma was 25 kilograms.
25.
Okay. Now, radius of Noah was 1.6 meters, but it's actually negative. And then radius of Emma.
We don't know.
Okay, we don't know that one.
That's what we're looking for.
Exactly what we're looking for. Now, we just have to calculate the center of gravity, right? We're going to use the center of gravity equation. So xcg. But where's the position of the center of gravity? It's at 0. So this is 0. Okay, now we can use the formula. So it's always x1 m1 plus x2 m2 plus x3 m3 and so on. Okay? So x1 m1 would be mass of Noah times radius of Noah plus mass of Emma times radius of Emma. And that's it.
Divided by
Mass of Noah plus mass of Emma. And that's it.
So then we just solve that equation for RE.
So we're going to solve for radius of Emma because that's what we're looking for. That's right. Now, because we have equals 0, okay, and that's the reason that we have equals 0 is because we chose the origin to be 0 at the center of gravity, right? Which is really convenient. That was smart to do. That gave us this equals 0 here. We can multiply the entire thing by the denominator and it goes away. Okay? So now we have 0 equals mass of Noah, radius of Noah, plus mass of Emma, radius of Emma.
So now what if we didn't choose that as a point?
Then the math wouldn't be as simple, but we could still get the answer if we didn't choose the origin to be the center of gravity at the pivot. Okay? Which is fine. We would just have more work, more math. We'd get there though. Okay? This is just convenient. So now just solve for r sub e, radius of Emma. Okay? So this one here goes to the other side.
It becomes negative.
Negative.
It was negative.
It was negative anyway, so now it will be positive. So negative m n r n. Now we're going to divide by mass of Emma. And we have radius of Emma. So we can plug in our numbers now. And notice that if we were plugging in our numbers earlier, we would probably not have seen how this is going to play out in a simpler way. So we have negative. Now mass of Noah.
22.
Radius of Noah.
Negative 1.6.
Now divide by mass of Emma.
25.
Notice that the kilograms are dividing out, so we're left with just meters. Negative times negative is positive, so this whole answer will be positive. And what do we get?
$1.4.
Okay, 1.4 meters then is where she should sit to balance the seesaw.
Just imagine for your significant figures in this stuff in your life. We're at 70 some, and we only got one significant figure. Now we gotta go to 100, something like that.
Yeah, well, we wouldn't do that, but yeah. So on the playground, she's gonna figure that out just using by feel, right? But now we know exactly where she has to be, and we could have marked it, ahead of time or whatever, and been like, I knew that already. Look at that mark, or just go sit right there.
Stuff in kindergarten because I don't see myself going to seesaw anytime soon.
Right. Okay, so now here's the human body. We can segment the human body or chop the human body up if we're sick people. The center of gravity of an extended object can often be found by considering the object is made up of pieces. So here we have segmented the body up into pieces, each with a massive center of gravity that are known or can be found. Then the coordinates of the entire object of the object center of gravity can be determined using equations that we've seen and used. So we have each segment of the body. So the hand, the forearm, the upper arm on both sides, the foot, the lower leg, the upper leg on both sides, and then the torso. Also, the head would have a center of gravity as well. We can find all of those locations for the center of gravity in the X and Y direction, and then find the actual center of gravity for the human body. Okay? And we can do that for each individual person. So that's the idea. That's how you would find someone's center of gravity.
I was wondering where the center of gravity symbol looked familiar from, and it makes sense now. So the test dummies you see those symbols.
Yeah, you're exactly right. The crash test dummies have those symbols on them. And that's why they have those symbols on them. It's for the exact reason. That's the exact reason. Okay, so now the gymnast performing on the rings holds himself in the pike position. In order to do that, he has to line up his center of gravity so that he is directly lined up with the rings. If he doesn't do that, he shakes and wobbles and he's all over the place, and it doesn't look nearly as clean, and he loses points because of it. So it shows how we can consider his body to be made up of two segments whose masses and center of gravity positions are shown. So I actually didn't show them, so we're going to draw them kind of on the side. The upper segment includes his head, trunk, and arms. So that is here. And then his lower segment consists of his legs. So that would be here. Locate the overall center of gravity of the gymnast.
So it's going to be right in the middle.
So his center of gravity for his upper body is right around this region. And then his center of gravity for his legs, his lower body, is right around this region. So where is his overall center of gravity then? Well, it's actually on a line directly connecting those two centers of gravity. Okay? So his center of gravity right now in this position is actually outside of his body slightly, right about there. And if you were to look, if we were somehow able to turn this picture to the side and look, you would find that this center of gravity is perfectly lined up with the straps on those rings. And that's how he's able to balance himself in the way that he has himself balanced. It's actually more of a balance problem. Of course, he's very strong, so he's able to do that. But it's more balance than anything, okay? If he did not have this center of gravity lined up with those straps, then he would be not able to control his body, and he'd start shaking and wobbling and probably fall. So that's how he's able to do that. This upper part of his body is actually outside of those straps. slightly to account for the fact that his center of gravity is matched up with those straps. Okay? That's how that's able to be done. So he has mastered his center of gravity. Gymnasts have a very, very good control over their center of gravity, and they're well aware of where it is at all times. And that's how they're able to do those tricks that they do on the floor or on the beam or on the bars and on these rings. Okay? Of course, with a great deal of strength and control. So another one that we'll talk about, I might as well talk about it now, is tightrope walkers. You have enough balance to walk on a tightrope?
And the Wii stuff, yeah.
The answer is no, nobody does. Okay. What do tightrope walkers have with them when they walk on a tightrope?
Their arms.
Arms are holding a what?
Weight. Rope. Helmet.
You have no idea?
No.
Okay.
Almost.
They're holding a long beam that at the ends has like a big like sphere on it. Okay. And that sphere has mass. So what's happening is, as the tightrope walker, I'm just going to draw really simple. So here's the rope, right? And then the tightrope walker is like this. And then they're holding here this long, flexible beam. Okay? It's like a long bar. And at the end of that bar is these two big masses here. What does that do for them? It lowers their center of gravity. Okay? Because if I'm trying to, like, imagine trying to balance a bat in your hand. I'm sure you've all done that, right? Is it easy?
No, you got to sit there and move.
You're moving, wobbling all over the place, right? It's terrible. But if you took the bat and turned it so that the thicker part was down, is it easier or harder?
Easier.
It's easier. Why?
Because now you don't have so much weight on top.
Because the center of gravity is lower now, right? So I'm standing here and I'm trying to balance all of myself on this stupid wire. I have terrible balance, but what has happened now is my center of gravity has been significantly lowered. My center of gravity normally is up here somewhere, right? But with this long beam, with these huge weights out here on the ends, what has happened to my center of gravity? It's been dropped down to somewhere around here. And now, even though I'm tall, I can walk a lot more easily on this wire because I can control and not wobble nearly as much here. Okay? And I can correct much more easily if I do start to wobble, because if I wobble, I can tip over, even this much, and my center of gravity hasn't shifted off of that wire too terribly. And even if it did, I can adjust this beam a little bit and drop this weight way down over here and correct my center of gravity to the point where it's actually still on top of that wire. So that's why those high rope walkers or those people who do those tight ropes carry that gigantic bar that's really flexible with the weights on the ends of it, because they've shifted their center of gravity down so low that it's actually made it way safer.
So could you do that with a log? Or does it have to be...
You wouldn't do it with a log because the log is not flexible. Your log would be up here, and although you would have made your base of support a little bit different, we haven't talked about base of support yet, but you would have not shifted your center of gravity anywhere unless you were able to carry the log lower. This very flexible bar has shifted the center of gravity down very, very low. This log would have made your center of gravity still very high and not made you balance any easier. Okay. If you saw a tightrope walker walking across the Grand Canyon without this flexible bar, that would be a lot different. Okay. This is the reason why when you're trying to balance on a thin something or another, you put your arms out. It's helping you correct your wobble. It's not doing much for you as much as this long bar would, but it is helping you. And it's the reason why shorter people have better balance than taller people, because their center of gravity is lower. So it all has to do with center of gravity. Okay. Anyway, that's the section. I thought you would be interested in that.